Thanks. Okay. Next, I am going to teach about a Eutectic phase diagram. In previous isomorphous phase diagram, the temperature between the uh, melting point temperature is vastly different. For copper, the melting point temperature copper is 1085 degrees Celsius and nickel is 1483 degrees Celsius. So therefore, the difference between the melting point temperature is vastly. And now in electric phase diagram, the temperature melting point temperature of the two components are not vastly different but limited solubility in solid state. Okay. In isomorphous phase diagram, the two components are completely soluble in both liquid and solid state. But in reactive phase diagram, the two components are not in solid state. It has the limited solubility. So it produces the intermediate components. Okay. So in binary phase diagram, the diagram plateaued between the temperature and the composition. So the composition taken along x-axis Okay. So this is a eutectic phase diagram for lead and a tin system. So in this eudectic phase diagram, the system contains tin is the solute. Tin is the solute. So in solid state, the lead is in maximum rich in solid state. Okay. So therefore, this phase diagram has three two-phase region such as L plus alpha, L plus beta, and alpha plus beta. Okay. And then three single phase region L, alpha, and beta. Okay, so that before that, the eudectic phase diagram is drawn by using the composition of lead and tin. This is PP. So SN values, the tin value is increases from 0 to 100. Okay, and the amount of lead will be slowly decreases from 100 to 0. Okay. In all the phase diagram, the composition axis is represented by the solute. That is the amount of tin or amount of solute values. Okay. So in this reductive phase diagram, it has three single phase regions L liquid and two solid phases alpha and beta, because solid are limited solubility. The solid in solid solution, it has limited solubility. So the in liquid state, both the two atoms are completely soluble or completely miscible in liquid state. In solid state, it exhibit a different crystalline structure or different state. Okay, so therefore it exhibit two different state, alpha plus beta. Okay. And then eudectic reactions nothing but upon cooling, or during cooling, the liquid has been varies from alpha plus beta. So in solid state, it has two different limited solubility. So therefore, it exhibit two different solid state. Okay. During heating, alpha plus beta gives a liquid state or L. So this is a eudectic reactions. This eudectic reactions takes place at 183 degrees Celsius. So this is called as eudectic temperature. So at this temperature, the liquid and the eudectic composition EC is equal to 61.9 percentage of tin SN. So at this composition, the liquid or upon cooling, the liquid changes from liquid to alpha plus beta, alpha plus beta. So this is called as eudectic phase diagram. Eudectic phase diagram. So the eudectic reactions take place 180 degrees Celsius and a 61.9 weight percentage of tin. Okay, and then it has a three two-phase region and three single-phase region and six boundaries. So this electric phase diagram uh, having the six boundaries. One is liquid as one, and this is the liquid as two. So liquid as one is between the boundary. Liquid one is the boundary between the liquid and the L plus alpha, and liquid as two is boundary between L plus beta and solid as one and solid as two. So solid as 1 is the boundary between alpha and L plus alpha, and solid as 2 is the boundary between L plus beta and beta, and two more boundaries solvers. So solvers is nothing but the boundary between the alpha and alpha plus beta, and solvers 2, the boundary between alpha plus beta and beta. So these six boundaries are there. The melting point temperature of pure lead is 323 degrees Celsius, and pure tin is 237 degrees Celsius. So the melting point temperature difference between the two components are not vastly different. So, and then uh, at solid state, the given components are having limited solubility. So therefore, it is boundary as separated regions. Okay, the alpha plus beta are the both the lead and tin does not completely soluble in solid state. They are produce a grain boundaries. Okay, they are produce a grain format or different crystal structure format. So therefore, it does not mingle or does not miscible. Okay. Then, so using phase or gives the phase rule, we can easily find out the degrees of freedom for the two phase region and the single phase regions on the boundaries. Okay. Mhm. Now, yes, this eutectic phase diagram. Within this phase diagram, uh, the left side, this is called as eutectic composition. Eutectic composition. This is called as a hypo, and this is called a hyper. Okay. Um, before exactly 183 degrees Celsius is the specific or temperature for the eutectic reaction takes place. Eutectic reaction takes place. So, at 183 degrees Celsius is the finest temperature. It varies from liquid to solid. Liquid to solid. So exactly 183 degrees Celsius, the liquid has been changes from liquid to solid. But before the composition value of 61.9 or 6.5 or this region or in this region, the yeah, the lead tin is also lead is easily stored lead is stored the solidification. So therefore, before reaching the 183 degrees Celsius, the lead has to start the solidification. So therefore, this solidification is called as pro-erectic alpha. Pro-erectic alpha is nothing but before 180 degrees Celsius, these lead or these substances are start the solidification. So therefore, that solid is called as pro-erectic alpha. Pro-erectic alpha. So alpha denotes the lead and beta denotes the tin. Okay. So before reaching the 180 degrees Celsius, the lead has to start the solidification. So therefore, this alpha has nothing but pro-erectic alpha. In the another region, pro-erectic beta. Okay. So left side of the erectic region is called as hypoerectic, and right side is the hypererectic regions. Okay. So, okay, that's it. Thank you.